Morning, everyone. So we're going to continue on our study in Chapter 3. Up to this point here, over the last 2 days, we've been looking at physical periodic trends. I'm just going to quickly draft the periodic table for you. Let's see how we do with these periodic trends here. We saw that throughout the section here, there were two main principles. One was the notion of Z effective. Z effective was essentially, what is the real nuclear charge? How many protons was I supposed to see? This is here from the core, the protons, but I have to minus off any electrons that are shielding or screening electrons that are closer than me. We saw that the Z effective increased going across here. As you step across, we go from having, let's say, one proton, no shielding shells here, lithium here. Lithium actually has two shells. By the time you go, I was supposed to see all three protons from lithium, but I minus off the two on the inside shell, that also gives me a +1. We can actually find Z effective fairly easy just based on the column number. So Z effective +1, +2, all the way through +3 and +8. Remember, these Z effectives here are not the real charges that things bond with. So for example, noble gas we'll see in today's lesson, they don't bond. They have zero charge. But at least when we deal with the Z effective notion, when we deal with how much leftover positive do the outer electrons feel, at least it has a full +8. Z effective here increases going to the right. Your reasoning here, you can mention here, we're getting more protons, not any additional screening electrons. Going downwards here, unfortunately, the Z effective stays fairly similar. Don't say the same. It's a little bit hand-wavy math. Electrons on different shells might screen differently. But in this case here, Z effective remains, I'm just going to use the terminology, they're similar. However, in terms of the radius that we do for radius, we just said, well, first shell only has one. Second row here has two shells, and we have three shells. Just the sheer number of shells would then increase my radius. So in this case here, let's just track this radius trend. Let's point that diagonal arrow. I'm going to still point the arrow, let's say up and to the right. The trend that we found was the radius actually decreases in this direction. The radius decreases. Your explanation cannot be, I've just memorized that side is small and this side is big. Your rationale has to use terms like Z effective, like number of shells. In this case here, we have higher Z effective or greater Z effective, or we have less shells as we head in that direction. If you can define for me something of radius, it's fairly easy talking about ionization energy. Ionization energy is how hard is it for you to remove electrons. Well, when the atom is very large, that electron is held very loosely. We see that from our second principle, which is Coulomb's law. Coulomb says F is QQ over R squared. These QQ is actually going to be relative. It's sort of representative of the Z effective. But whereas as the radius increases, let's say I have way more shells, the force is going to drastically drop. Meaning these protons here have a hard time hanging on to the electrons. Not only did that mean their shells will converge in the earlier chapter, it also says, oh, just give it a quick bump, and this one's very easy to lose. So these have relatively low ionization energy as compared to something that's big. So therefore, going up and to the right, as things become more and more non-metallic here, the ionization energy increases. It gets harder to remove because of smaller radius. Anytime you use radius as a trend, I would still quote smaller radius. Oh, it's because we have higher Z effective, less shells. I would still define why I know it's tinier atoms, but that's just a nice reminder for yourself. When we looked at trends of electron activity, electron affinity here, electron activity was this tug-of-war strength. Again, not only am I trying to hold on to my electrons and trying to keep them from being ionized, the protons here are trying to tug-of-war electrons. Let's say these atoms here collide together. They actually want to steal electrons or gain electrons from other. Again, the further out they are, the worse I am at tug-of-warring. I'd rather be a tinier atom, which is why nonmetals typically pull harder. The electron activity is going to increase for the same reason as we get smaller radius. The EA is electron affinity, sort of an opposite of ionization energy. If I have an electron at infinity, we saw in yesterday's lesson, even though the metals don't technically want the electron, it's a lesser of two evils. Fine, you can come home, fine. I'm going to attract this electron. You can stay close by my nucleus, so then we can actually keep an eye on you. So that's actually going to release a little bit of energy compared to adding it to something that's tiny. Sometimes halogens actually pick up a noble gas configuration once they gain this electron, but even if they didn't, because the halogen or other nonmetals are a fairly small radius, those electrons that get added are a lot closer to the core. They have more stability. A smaller radius means a stronger force of attraction. I'm stabilizing that added electron more, meaning more energy can get released. So the EA, the terminology we're going to still say is EA increases. The numbers were a little funky. We had negative 60 kilojoules per mole. Yesterday's example, I think we had negative 348 kilojoules per mole. We know that first electron affinity will be negative, so it's almost like I ignore this for a second. We know it's going to be exothermic, but we just look at the size. Metals, the metal that I used yesterday, it released 60 kilojoules, whereas for the non-metal, it actually released some 7 times or 6 times that. So more energy. I prefer the language of being more exothermic. That's not a reason. Again, the reason comes down to the size. If I'm a smaller size, I end up attracting the electrons better, gaining the electrons better. Same thing with EN increases. I know it means I'm stronger at tug-of-warring, but that doesn't explain anything. Your explanations all have to go down to what do you know about the size and how do you know about the size. So EN, EA increases. We saw melting point as the worst trend. We're going to do this as a warm-up question here. Melting point, because we're trying to separate species from species, we're actually trying to break up what are called intermolecular forces, the forces that are in between compounds. They really like asking the melting point question in this fashion. I want you to state the melting point trend down your alkalis and compare to halogens. Okay, so they're specifically picking out 2 groups. We're going to, in this lesson, start switching over to the chemical reactivity. But basically, they're saying in our rough periodic table like this, what happens to the melting point as you go down the alkali family? The alkali family is group number 1. We know the sizes of them go from like lithium with 2 shells, sodium with 3 shells, 4 or 5. Like we know that happens to the size. What happens to the melting point going down this way? That's group number 1. That's our alkalis. And technically group 17, or valence electrons group 7, we can call these ones the halogens. Again, size-wise, fluorine will have 2 shells, chlorine will have 3 shells. Size-wise is the same, but because these are nonmetals, they're going to do a different type of bonding. We couldn't memorize just one side was really hard to melt or the other side was easier to melt. We actually had to look at what type of bonding that they had. If you remember from yesterday's notes here, for your alkalis, they would be an example of the metallic bonding section. For a metallic bonding, this was purely a KQ over R squared. So it's a Coulomb attraction. And basically what you can argue here, for a metallic attraction, because the radius increases as you go downwards, as the size gets larger and larger, we square it, gets even bigger, I divide it by a bigger number, the force of attraction actually gets weaker. So if you compare, let's say this lithium case here, lithium's atoms are a lot more tiny than, say, the francium case. It's the same mechanism. The metallic bond is between the positive nuclei that are sort of stuck in place in trying to attract the delocalized electrons that are just swimming around their neighbors. But in this case here, because francium has to reach quite a bit farther out, the radius is bigger, the attraction for those neighbors are going to be weaker. So we would expect the melting point to actually decrease going down this way. So your language here is going to be melting point decrease. You can quote the type of bond. Metallic bonding is weaker as radius increases. That's a reason. Okay, you can even qualify radius increases because you have more shells. You can't give more, like too much information. Just make sure everything that you write is consistent with each other. Melting point decreases, so melting point drops, so it's easier and easier to melt. We're going to see in today's lesson that actually makes the lower alkali metals even more reactive. Unlike your halogens, though, we're actually going to see the melting point trend is actually the opposite. The melting point, if you look at section number 8, the melting point for your halogens actually increases, as verified by, if you look at fluorine and chlorine, at regular conditions, these ones here are gases. That means by room temperature, it's already melted and even boiled off. When you get to your bromine, bromine is actually just a liquid. Sure, it's melted, but I haven't even boiled yet. By the time you get to iodine in the same condition, iodine is actually a solid. Yes, iodine is still a nonmetal. We just had a generalization. Nonmetals are typically, or covalent compounds are typically gases or liquids, but it's not impossible for a nonmetal to be solid. So in this case here for iodine, the melting point has increased so drastically that it's still a solid at room temperature. I thought the atoms were getting bigger. How come it's actually able to hold itself together better? It is true, there is that compromise. When you do think about F as KQ over R squared, you're totally right that small atoms should have small radius, stronger attraction. These ones here should hold themselves together better, but you have to be careful when you look at the halogens. Remember, we're actually not trying to destroy a fluorine-fluorine covalent bond. We're just trying to destroy what I introduced you yesterday as London forces. There are some background attractions. The positive from one fluorine not only holds on to its own negatives, it's attracted to the electrons on the neighbors as well. When I try to melt it, I just try to heat it up enough that the groupings are shaking hard enough that I can separate molecule from molecule. It is true as I step my way down to iodine, we did this example yesterday as well, it's true that this iodine, all these core protons here are actually having to reach farther out. Dollar for dollar, each of these attractions are weaker, but we also need to couple it here. Fluorine here is 9 protons, whereas iodine is 53 protons. So even though this London force here for one proton might actually be weaker because I'm actually having to reach farther out, let's couple that here with a lot more protons. Every single one of these protons has a similar weaker attraction London force with their neighboring electrons. Just the sheer number of London forces will increase the strength between, so it's going to be harder to then melt. So yes, increasing radii should have meant the force is weaker, but because these guys here use London forces, you can use the terminology here, quote the type of force that they do. Halogens do London forces. London forces are actually stronger with more charges, more electrons, and usually we measure the number of electrons, just track the molar mass. Typically, mass doesn't have anything to do with electrons, but if I have something that's heavier, that generally means I'm either elements that have more protons or coming along with more electrons. Especially when I make comparisons between melting point, first thing I want to check is their molar masses are similar. I want to make sure that they're all easy to compare with each other, and then I look at what's the in-between force. We'll do that a little bit more in Chapter 4. So you notice the melting point trend, not only is it not as well defined, you do have your melting points, you do have your melting point numbers actually quoted for you in the data booklet, but we'll go from there. Okay, so that finishes off the physical trend section here. Make sure you're comfortable with explaining, defining those terms like electronegativity, like ionization energy. We're going to now switch over in the next 2 lessons to look at chemical reactivities or chemical properties. So we are interested in still periodic patterns. We're still saying when Mendeleev organizes the periodic table, what sort of commonalities or what sort of patterns actually exist. For chemical properties, we're going to bank on this, that chemical reactions or how reactive something is, the reactivity of anything depends on the valence electrons. It depends only on the outermost electrons. We saw in the earlier chapter, the outermost electrons are only the S's and the P's. Those are the only electrons that the Bohr model is able to draw. So if you can tell me something about my outermost shell, I can tell you something about the commonality in reaction. The reason why it is outermost shell here, if you imagine for elements to actually react, atoms themselves actually have to collide together. So whether this atom here has, let's say, 2 or 3 shells or whatnot, it's always going to be the outermost layer actually colliding with the outermost layer anyways. All those inner electrons, we call those core electrons, they just come along for the ride. They don't matter. So even though, like for example, let's compare hydrogen. Hydrogen only has 1 shell. It has 1 valence electron. Let's collide it with sodium. Okay, sodium has 3 shells. Because they equally have just 1 valence electron on their outermost shell, they're going to behave in exactly the same fashion. Most of the collisions actually result in no reaction. There's a certain activation barrier we're going to see in Chapter 6 to actually talk about reaction being successful, but at least we do see that it's the outermost electrons. So today I'm going to introduce to you 2 common families along with their reactivities. For the alkali metals, I'll also join it to another YouTube clip where you can see some of the more drastic trends that we see. Let's start off here with the easiest family here. So we have our rough periodic table here. IB likes calling the noble gases here group 18. You can sometimes call them group 8 for the number of valence electrons. Sometimes because when they bond, well, they don't bond, they have a charge of 0. Sometimes you can even call them group 0. So we're going to start off this lesson looking at your noble gases. Once we're done looking at the noble gases, we're going to look at column number 1. Column number 1, which are alkali metals. If you look at the element number, column number 1 could have actually been right beside the noble gases. For example, helium is element number 2. Lithium is element number 3. I could have put lithium right beside it. Although I don't want my periodic table to be infinitely long, you do want to track that the alkali metal family is sort of like still one group away from noble gases, which makes them the most reactive metals that we have. So without further ado here, let's look at the families here. Let's start off with our noble gases. In the past, they used to call these noble gases inert gases. The word inert meaning they never react. Okay? We found that in the last 10, 20 years or so, under really dramatic circumstances, you can actually force noble gases to actually bond. It's sort of against its will there. It's going to actually, it already had that full gas stability, full shell, but you actually force it to bond to other things. So noble gases here, you can call it group 18. I mentioned already, you can call it group 8, even call it group 0 if you like. This one here is looking at the helium, neon, argon, krypton, xenon, and radon. Okay, so those are those 6 there. You don't need to memorize those. You have the periodic table for them. Some common characteristics that you want to know for the noble gases. These ones here all show up as monatomic. Most of my elements showed up as monatomic, meaning they all occur as single atoms. Well, there's no reason for them to become diatomic or bond with other things. Of course, they come as single atoms. They just might be different numbers of shells. Their radius still might be different. But overall, they're monatomic. They come as single atoms. They are all colorless gases. So unlike the halogens we'll see in the next lesson, halogens are typically colorful. These ones here are invisible to us. They're completely colorless. And as we've already been calling them, they're fairly noble. They keep to themselves almost as if they were inert. These are the least reactive elements that we have on the whole periodic table, especially our nonmetals. Although we don't have a full justification of this, we've just been believing this fact here. The reason why noble gases are so stable is because they already have a full valence shell. It's the outermost electrons, it's those valence electrons, the S and P, that actually do the bonding. I already have my fill, I already have my octet satisfied, I already have all the electrons that I want. I don't really want to gain or lose electrons or share electrons because I'm happy. The language we're going to use in the next chapter, I just mentioned it here, it satisfies the octet rule. Octet reminds us 8, and with the exception of n equals 1, which maxes out max on the n equals 1 level, max of 2 electrons, then 8, then 8. Most of our shell is maxed out at 8, so that's why we can say octet. In fact, there's something about having this full shell that makes you stable that every other element is jealous of it. So we're going to see alkali metals in a little more detail, but when you look at metals in general, metals have a full shell and the odd electron more. They may have 1 to 2 to 3 extra electrons. If only these electrons can get lost, then I can look like a noble gas, then I can have that full shell, then I can be enjoying that same stability. The number of electrons that I lose would depend on how many outermost electrons that I have. So just a generalization here. Metals, this could be alkali metals, but even beyond there, let's look at groups 1 through 3. Metals tend to lose electrons. The fancy language is oxidized. They get oxidized to look like or to resemble a noble gas. They want to have that full shell stability. You've probably used in your Science 9, Science 10 courses here. Let's do lithium as an example. Lithium as its Bohr model, it has those 3 electrons. We're focusing just on this outermost shell. In this case here, you probably use the argument, well, is it easier to lose 1? Right? Or if I want a full shell, gain 7, well, just a sheer number argument. You say, oh, losing 1. We actually, based on our physical trends, we can actually qualify that a little bit. Because lithium is so far on the left side, lithium is going to have the lowest Z effective. It's going to have relatively the largest radius. And because it has such a big radius, it means it's going to have a relatively low ionization energy. So not only just a pure numbers game, was it easier to play around with 1 electron or try to gain 7 to completely fill up, we actually, because we have a big radius, it actually is, for metals, easier to lose this electron here. So there's lithium. By losing that 1 electron, I didn't touch the core, so I'm still going to be lithium. I now have still the 3 protons and 2 extra electrons. I'm now a lithium plus 1 ion, and now I've lost an electron. I've reverted down a shell. I don't bother drawing shell number 2 anymore, but I now am isoelectronic with helium, and I'm now stable. All metals typically oxidize and lose electrons until they look like this. Similarly, for other things like beryllium and boron, they may have 2 shells, 2 valence electrons, 3 valence electrons. They typically are also the larger radii. You might need to ionize it more than once, but they're going to eventually try to look like this, try to look like their closest noble gas. Non-metals in contrast. So non-metals, the handful of them we have on the right-hand side. This one here, technically, we should say groups 15 to 17. We usually call them group 5 to 7. We never talk periodic trends of the actual 5th column and 7th column. So you just know when I say 5 and 7, I'm actually talking about 15 to 17 because I'm just focusing on the valence electrons. I'm ignoring those d electrons. There's 10 of them in between there. So in this case here, non-metals, these guys here, because they're tinier radius, their Z effective is higher, their electron activity is bigger, so they're much better at tug-of-warring electrons. Electron affinity is more electron affinite, so they can gain electrons. We can use that language, gain electrons, until isoelectronic, until they look like the closest noble gas. They're not transforming into the noble gas. They just have played around with the number of electrons so that their outer shells resemble what a noble gas shell has. So just to show you that this happens for other nonmetals as well, let's do oxygen. Oxygen also has 2 shells here. We still do our Bohr model, right? So we have oxygen there. O is super unstable here. It's a radical. It has these unpaired electrons. Because O has a small radius, remember always to explain why the radius is tiny. In this case here, it has more Z effective than any other thing on row number 2. Because it's tiny, not only can we say, well, is it easier to gain 2 or is it easier to lose 6? Because I'm tinier, a nonmetal naturally wants to hog electrons, gain electrons towards itself. So if I first electron affinity it, if I give it this electron here, it'll feel more relaxed because it's closer to noble gas configuration. Because oxygen is a small radius, it can stabilize that electron fairly well. Because I've then ended up forming a negative charge, it may not be spontaneous for another electron forcefully to come in, but once that second electron comes in, once I do the second electron affinity, I end up getting the O with the 2 full shells. I now am isoelectronic with neon. Because I'm charged, I'm going to still put the charge in the corner there. And there, once I'm have the full shell, I actually had to gain these 2 electrons, so plus 2 electrons. That's an indication of a reduction reaction. So metals get oxidized, they lose electrons, and non-metals, they gain electrons. All of them are trying to look like a noble gas. We can just emphasize noble gases. We already said the full shell gives you stability. The noble gases are really stable because they have very high ionization energies. Noble gases typically are the smallest radii per row. Okay. If you actually look at the numbers, there's a slight exception. Sometimes your halogens are a little bit tinier, but I'm just going to do a generalization here. Because they have very small radius, that means they have very high ionization energy. They have a really tight hold on all their electrons. Not only do they not want to lose electrons to lose that full shell stability, they actually are a tinier atom. When you do KQ/R², they're pulling on their electrons much more tight than something that's larger. High ionization energy, they already are full, so they really have no desire. They have a good, so also a high electron negativity, right? They wouldn't naturally want to be electron affinite, so they're good to just hold on to the electrons that they have. They're good, they just keep to themselves. So that's why noble gases are fairly unreactive, and whether I'm a small noble gas or a big noble gas, I'm going to still be inert, I'm going to still be unreactive. Such is why we're actually not given electronegativity values. These ones here don't really bond. High electronegativity, we really only saw it on the table for things like xenon. Again, within the last 10-20 years or so, we forced the heavier noble gas to actually bond. The lighter noble gases actually have no chance of bonding. So that's it for noble gases. Let's switch over to look at halogens, our most reactive metal family. We already saw what the type of reactivity is going to be. We're going to look at alkali metals here. Alkali metals, we are looking at group number 1. If you look at the periodic table, although hydrogen itself is actually also in that first column, hydrogen is included because it likewise has a valence electron. Hydrogen is not an alkali metal. So for for alkali metals, we actually start from row number 2. We start from the lithium, and we go all the way down to the francium. So alkali metals here, I'm not going to list all of them for you, but we're looking at lithium all the way down to francium. If you Wikipedia it, for some reason, francium, based on its stability, you can't really collect a lot of it at any given time. So sometimes they totally ignore it, and sometimes they say cesium, the one right above it, is the heaviest noble gas, but definitely towards that side on the periodic table. So first thing we want to know here is for these alkali metals, how do these things here hold themselves together? We know metals are typically solids. at, I'm just going to say room temperature pressure, our regular exposure of them, these ones here are actually solid, that must mean that they're intermolecular forces, that the species themselves are actually holding other neighbors much better. This is another hashout of alkali metals do metallic bonding. When you're defining metallic bonding, I've written the definition a couple times now, but let's go again. Metallic bonding is an electrostatic attraction. It's a Coulomb attraction. It's a positive negative attraction. Whenever you talk about Coulomb attraction, you just want to identify what's the positive and what's the negative. In a metallic bonding case, remember, we're not ionic. We're not Na plus Cl minus. I don't actually have real charges, cations, and anions. There was no electron transfer. What I actually just have is metal, 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 metal. The metal atoms are just side by side. So electrostatic attraction between, even though I may not have transferred electrons, I do have positive centers. Those are sort of stapled down. Those can only vibrate. They can't really move around. Positive nuclei, and the terminology is delocalized electrons. I know it's going to be protons in the nucleus attracting electrons, but specifically in the metallic bonding case, these electrons are delocalized. Again, let's rehash that here. Let's say someone hands you a block of lithium. So that means atom for atom, it's just lithium, lithium, lithium. Notice that there are no nonmetals in sight. So it's not actually an ionic bond. No one really gets a full positive, full negative. And yet what we're going to have is the centers are all positives. Those are positive nuclei. The centers are definitely hanging on to the electrons of their own. Lithium on average should have 3 electrons. But what we're going to say here is metals, we'll do this again in chapter 4, metals generally have they have the biggest radius per row. And that's because they have a low Z effective. You see some of those physical trends that we talked about come back and help justifying this. Because they have a very low Z effective, that means they're going to have a very low ionization energy. It gets even lower as the metal gets larger. But low ionization energy implies it's easy to push off an electron. And because I'm so large, I'm having a really hard time with a low electron activity. I can't tug of war my electrons back. I can't gain my electrons back because metals don't really want to become negative. Sure, my electron may be able to absorb to some degree, but the amount of stability I give it is nowhere near what a non-metal could give it. So in this case here, it's easy to dislodge an electron, and it's hard to, let's just say, regain, hard to grab that electron back. So we've been saying electrons feel really unloved. Every electron here, although on average every metal was supposed to have a bunch of electrons, the electrons here are actually going to be delocalized. They can swim through the entire structure, which actually explains why metals are actually conductive. Electrons have a negative charge. They're able to swim through the bulk sample. They've now been delocalized. They've now been shared. What I picture here is, imagine instead of electrons being stuck down to any given atom, imagine I have a bathtub full of electrons, and the electrons sort of form a pool, a water of electrons. It's an electron sea. The electrons are just every which way. There's just non-directional bonding between positive and wherever the electrons happen to end up. Metallic bonding ends up being fairly strong, which is why, in this case here, it's typically solid at room temperature pressure. So we have that delocalized nature there. Some conclusions there. We already said that it's solid at room temperature. Solid implies that it has high melting point, high boiling point. You would need to take these pure metals upwards of 700, 800 degrees before these melt. Here are some other common physical characteristics, and then we'll switch over to the chemical. Surprisingly, these are very soft metals. On the YouTube clip that I'll link on our Google Doc, you're going to see that they're going to take a scalpel knife, and it's almost like cutting butter with a butter knife here. Really, really soft, really, really low density metals. So that's just a physical characteristic. It's definitely going to be shiny and metallic, conductive, and all those things there. But those two are specific to alkali metals. These ones here, I want you to make a note. These are the most reactive metals because they only need one electron, and then they're already a noble gas. Alkaline earth metals are sort of somewhat reactive, but they need to lose 2 electrons. Most reactive metals because they only need to oxidize. I'm going to use that language of reduction and oxidation. Oxidize meaning lose electrons. Oxidize 1 electron to resemble a noble gas, to be isoelectronic with a noble gas. Remember, the element is not transforming. I don't suddenly change into a noble gas, but at least my electron structure, my outer shells look like it's a noble gas. So in this section here, we are interested in this reactivity. We're interested in how things bond. You have to have some sense of how it's trying to bond for us to predict whether it's more active, more reactive, or not. So in this case here, for metals in general, and specific for alkali metals here, their reactivity, or the type of reactions that they like doing, it relies on the fact we're talking about trying to lose electrons, and it relies on the fact of having low ionization energy. For the reactions, for metals in general, alkali metals in specific here, we're relying on the feature of being low ionization energy. So if I go down my alkali metals, let's say I have lithium. I know lithium has 2 shells. Let's go all the way down to, let's say, francium and cesium. Francium has, I think, 7 shells. Okay, I'm not going to be able to draw all 7. But just a comparison here, by the time you work out your Z effective, lithium here has 3 protons. We're going to have screened out 2 of the electrons effectively. The Zeph is going to be +1. You can't say, well, francium, off the top of my head, I think it's element 87 or something like that. Okay, when I have 87, I can't just say, whoa, way more protons. Of course, way tinier. Remember, we also end up having a lot more screening shells as well. All these shells here block out the positive nuclei and leave you with the Z effective of +1. That would naturally imply to you, oh, we see the same KQQ from the core, obviously on the same reactivity. And yet, when you look at this diagram, we also realize as I go down the periodic table, I actually get more shells. So in this case here, I only have 2 shells. I'm a small radius. So small radius. As I go downwards, we're ending up picking more shells. We're going to get larger and larger size. And again, you will always want to qualify how do you know it's more radius. In this case here, it's more shells. So in this case here, if the reaction of all these ones here, alkali metals want to lose the electron, the property that we're interested in is ionization. All these alkali metals have just 1 single electron to lose, in which case will it be easier to actually lose this electron? If you think here F is equal to KQQ over R squared, it's always going to be this fundamental Coulomb attraction in the background. Although you might argue their Z effective is similar between lithium and francium, because the radius for francium or even cesium is way bigger, the force of attraction is way weaker. So this, even though I have way more protons in francium's core, because the core is having to reach out so far, it's having a really hard time holding onto that electron. Which means, given the opportunity to collide with something, given an opportunity to actually lose this electron, to revert down a shell and get that noble gas stability, this one here has a lower ionization energy. This one here is much easier to remove. So in that case there, we can just qualify here. We said the radius increases this way. Our ionization energy actually decreases as the size drops. And because metals try to react by losing electrons, because it's so easy to lose that electron, the reactivity of your non-metals, of your alkali metals, reactivity actually increases going down the periodic table. This is generally true for all metals. So on the periodic table, let's go up to one of my sketches here. On the periodic table, you would expect the metals, the lower regions here to be the most reactive. For non-metals, they react in a different way. So just memorize this trend here. The most reactive ones are the ones that are most metallic, are the ones that are farthest in the corner. When we see in tomorrow's lesson, the most reactive non-metals are actually the smallest ones. You can think about what the reason for it is, but we'll flesh that out a little bit more tomorrow. So herein lies the last part of this alkali metal section here. It's fair game for them to just quote a few reactants and then just say, just like we did 2 months ago, just predict the products. Some of them are going to be simple, those 6 easy types of reactions, easy to predict the products, and some of them you will have to memorize. Okay, so for your alkali metals here, the most reactive alkali metal is going to be francium because it's the largest, it's the easiest to pick off, the biggest radius. In terms of reactivity, they want you to know 2 types. One is the reactivity here. Alkalis react with oxygen. Okay, that's actually where we started off the term of being oxidized. We eventually saw it in terms of electrons. We'll do that a lot more in chapter 9. But electrons react with oxygen. In general, what that means is we're going to take our alkali metal, our lithium or francium. I'm just writing them as a generic M here. I can state that they're solids. We already talked about metallic bonding being strong. This metal here can react with oxygen. This one here is not so hard to predict because I have element and element. You predict that it would be a synthesis reaction here. And if you look at the charges here, I'm going to get M2O, right? The metal by itself, this one here is neutral, so don't put a charge there. But by the time it bonds, by the time it has a chance to collide, alkali metals typically take on a +1. Because oxygen has a -2 charge, I need 2 of the +1 to actually cancel it out. Eventually, the ionic ends up forming a lattice anyways, but at least by ratio, I need 2 alkalis per oxygen. Let's also balance that here. I need the 2 in front here, and I need 4. So this one I wouldn't bother memorizing because you can predict this based on just regular ode synthesis reaction. The next one here you will need to memorize because this one is a little bit harder to predict. Second reaction, you're going to see this on the YouTube clip that I linked to. Alkalis here actually react very violently with water. So let me give you the general equation again. We're going to have any alkali metal. I'm going to react it with water. Okay. Water, we always say water is a liquid. I never say water aqueous. It's not like water dissolved in itself. So water is a pure liquid. It has a constant density. So we have that. It's fair game for them to ask you what the products are in this situation. The way I hint it for myself and I try to create a memory aid for myself, I think of water, I know it's actually covalently bonded, but I think of water as being comprised of an H and OH. If I wrote this reaction, this should look a little more familiar here. Oh, this metal here is by itself. This H part is sort of acting like the metal. It's sort of looking like a single replacement reaction. So this is just a hint for myself. This is not what chemically is actually happening. But your alkali metal is actually going to swap places with the hydrogen. So that means we're going to end up with the alkali metal. The alkali metal has a +1 charge. So that alkali metal is going to be bonded with the hydroxide. So metal hydroxide. And then the hydrogen that got single replaced off, some reactions actually aren't even able to produce the hydrogen, but in general, we do get the hydrogen out in this product here. Let's again balance it here. I think we need 2, 2, 2, and 1. So check it, 2M, 2M, 2 times 2 for H's, 2 H's here and 2 H's at the end, 2 O's and 2 O's. I've just been using M for short. This could be anything. It could have been 2 lithium becomes 2 lithium hydroxide. I want you to memorize this equation here. By the end of this chapter here, we'll actually need to memorize about 7 or 8 equations. Not the end of the world if you can memorize them, but it is fair game for them to actually say, oh, here are your reactants. What might we expect out of it? Some of them you can just predict based on what we know already. Some of them there's little hints along the way. There's another hint for this one here. The reason we call them alkalis are a subset of bases, right? Like acid and base. For a base, we expect to see a hydroxide. So when you drop a metal, and because we call it alkali or alkaline, I would imagine that it ends up forming a basic solution. I would imagine it creates something that has hydroxide inside of it. We're going to spend a whole chapter next year actually looking at the broader definitions for acid and base, but for the time being, bases just release hydroxide. Okay, so that's it for our lesson for today. We'll look at halogens in tomorrow's lesson and go from there. Thanks, guys. Take care.